And let me give a review quickly about the things we're talking about here. So if we consider a shaft and with arbitrary cross sections, and prismatic, that means the cross section pretty much is uniform across the axial directions. Okay, so here in our notations, we using Z to denote the axial direction and XY like this. Okay. The first assumption we make is this: all the cross sections, if they do the rigid body rotation during the twisting. So that means basically build up is something like this. For example, say we start from this point, A is on the original undeformed shape. And after we apply the torsion here, then for example, A is twisted and displaced to A prime. Okay, so that means from here, we are able to define this angle. Okay, this angle is called the angle of twist. Okay, and then the angle of the twist, and let me define whatever, give a name, just theta. Angle of the twist, angle of the twist.
Alpha is usually alpha.
We use last time, what symbol we used?
We used alpha last time, I think. That's what I have written.
Because here we use quite a bit symbols here. So how about this? Just let me say using the big theta, okay, capital theta. And then last time we, for the first assumption is this: all the rigid body, all the cross section during the twisting is under rigid body rotations. Okay, so that means in this plane, XY plane, if this is a certain profile, for example, this segment here, then from A, this is the radius where the point move stay here. So then this point on the rigid body rotation move to here. Okay, basically the radius keep the same. Okay, so let me say this is again using the same, keep with the same symbols, A to move A to prime. So from here we'll be able to determine the displacement U and V, right? Okay. So that is the starting point of the shaft. Let's study the shaft here. And under these situations, the angle of the twist, and sorry, let me state with this one. And this is the under rigid body rotation on any point in the cross section. And we make sure in the XY plane, this kind of stick, the distance from OA keep the same as the OA prime. And that is based upon our first assumptions. All the cross section is under the rigid body rotation in the XY plane. So under these situations, we will be able to determine the UV, okay, displacement, vector, in terms of the coordinate. Okay, for example, here let me say A has the coordinate X and Y, okay, and say this is the angle, let me call it theta. Theta, basically from here you can imagine is this. You simply, theta is defined by this. For example, this is the length, the height, level Z, okay? And theta and the whole length of the shaft is L, okay? So theta in proportion, in proportion to that one, basically is this. The whole angle of the twist divided by L times Z, that's called the theta. So basically that comes to the second assumptions. We assume that the twisting pretty much is uniform across the axial direction. So that means for each cross section at a different level, the angle of the twist corresponding to that specific cross section basically can be predicted related linearly to the top one there. Okay, so basically here, this is about the second assumption here. Okay, and for this purpose and that one, we define this symbol as the beta, and beta is called the rate of twisting, right, or rate of the rotations. Okay, so theta equal to this one. Okay, so with this in mind, then last time we have come up with is this, and through the rigid body rotations, you can determine the difference between x prime and y prime. Right? So you can formulate the x prime, and x prime basically say is in terms of say, let me do additional. Okay, so basically you can figure out this one, and that one is what we did last time. Basically this can be related to is minus y theta and times x theta. So that means the x displacement, the displacement component in x direction through the careful arrangement like this can be equal to minus y theta, and v can be equal to this one. And how to obtain this one, please refer to our lecture notes last time, or in the handouts there. In details we provided. Okay, so keep those things in mind. Then hopefully we can relate everything in terms of x, y, z. So basically here, let me kick in the theta. Basically this is equal to minus beta yz, and this is beta xz. Okay, so to this moment so far we have applied the two assumptions. Again, the first assumption is we assume the point on the cross section is performing on the rigid body rotations. The second assumption is we take this kind of linearity in determining the angle of the twist on each cross section. That means through the second assumption we introduce the constant and beta. Okay. So everything will be ready to go. So for any point, and that is u, v, and right now we're talking is in 3 dimensions. So for example, at the point here, and the point has the xy coordinate xy, and this point has z. And so far for this case, we only talk about is the displacement in the xy plane. And from here, I want to add up the third coordinate, which means the displacement in the z direction. So that is called the w, and that's a function of xy. Okay. Good. For the third displacement, and we have nothing to talk about this the displacement in the z direction here. Everything we talk about on this portion here is based upon the xy. We have nothing about the z plane, so we shouldn't make any assumption on the z plane yet. Okay. For certain shaft, I can tell you that w will be 0 throughout the whole shaft. When w equal to 0, we call it there's a no warpage. Okay, we call the warping or call the warpage. That means non-zero component, non-zero displacement in z direction. Again, when w is not equal to 0, then that is called the warpage. W-A-R-P-A-G. So that's a special terms describing the distortions of these cross sections into z directions. Okay. So that keep this in mind. Then we begin to have this. So right now for this displacement, we have, let me plug in there. That is minus beta and yz and beta xz and this is W, and that is a function of xy. Okay, so from here, this one basically in general, the displacement is a function of x, y, z. The displacement is the function of the locations. For example, at this point, it has a coordinate x, y, z. At another point, has another coordinate x, y, z. So in general, the displacement here or here really depends on his locations in the shaft. You good? Okay. So keep everything, we move on here. And so once we have a displacement, so you can see, before we move on, you can see this displacement is better than nothing. Otherwise, before we proceed everything, we just assume the displacement is u, v, w, u is a function of x, y, or z. The same thing, that one. If we, without every assumption from the very beginning, basically those are implicit functions. But after imposing the assumption 1 and assumption 2, then we can have the explicit expression for the two components. So that's what I said, better than nothing. Okay, so at least this displacement component, this component that really we know exactly that is expression form, leaving this still implicit. So that is the effort we're going to spend on through the whole chapter here about dealing with this term. But keep this in mind, then before we're reaching the point how to deal with this one, we just move on to formulate all the possible information we know. Okay. So what is the next step? So we have the displacement, and then we have the displacement, then we know we can begin to calculate strain, right? We know the strain is related to the displacement. That is the very natural process from our previous chapters. So here we can determine, so for example, you can determine sigma x. So that is partial u, partial x, and from here you can see that is 0. And sigma y, you can also determine that is partial v, partial y, so that is equal to 0, and sigma z, that is partial w, partial z. Again, here we assume the that one doesn't depend on the x, so that means the warping. Here we impose the third one, the warping basically doesn't depend on the z. That means the warping, once occurred, will be uniform across the whole axial direction. So here we don't assume that is a function of z. Under that situation, this is 0. Okay. Then we begin to calculate xy. So that is partial u, partial y, plus partial v, partial x. So for this case, you can see this one will be equal to 0. Okay, plug in. And then for this one, that is the z, yz. Let me use in zy, okay. So this one will be equal to partial w and partial y plus partial v, partial z. Either way. Okay, so partial v, partial z plus partial w, partial y. Okay. So v is equal to this one. So basically that gives us is beta x plus partial w and partial y. Okay. And gamma zx equal to partial u, partial z, plus partial w, partial x. So that is, plug in the u equal to this component, so that is minus beta y, plus partial w, partial x. Okay, good enough. Okay. Then we have strength, then we can come up with stress. Basic stress is multiply the strain with the corresponding rigidity modulus. So from here, apply Hooke's law. We're assuming, how about this? We're assuming, for simplicity, we assume the isotropic shaft. Okay. Of course, if you like, you can extend to non-isotropic. But for isotropic, then basically you can see the ij will be easy to this form. 0, 0, and this will be g times the zx minus beta y plus partial w partial x, and 0, 0, g times beta x plus w partial y. And then symmetric, so this will be g and minus beta y plus partial w partial x and g beta x plus w partial y. Yeah. Okay. So again, refer to isotropic Hooke's law, and then you should be able to formulate the only two non-zero stress components are the xz, yz, the two components. Other one will be zero. Good? Okay. Then what else we can come up with? For two-dimensional, the compatibility of the strength is straightforward. You can apply for it, actually become trivial. For stress, we also need to concern about the equilibrium of the stress. And again, if you remember that equilibrium equations, and that basically is something like this. Something like, say, partial, let me make one. Okay, so sigma x. Okay, let me write it out, whole things. And here we don't have any body force, so that is equal to 0. And tau yx sorry Ben, I block your way, block your view. Okay, so that's the equilibrium equations, and we simply plug in. So by plugging, then we can see. So this term is equal to 0, and this term is this one equal to 0, and then this term is this one here, right? Tau xz. Derivative respect to z, nothing there. So basically, this term will be 0, right? Okay, and then for these equations. Again, partial x. This one is yx. Yx is this term, so that is 0. And partial y. And this is this term equal to 0. And partial z. And this one is tau yz. Tau yz is this term. This term takes partial derivative with respect to z. Again, this is a function, nothing z, so this one is automatically equal to 0. So the first two equations satisfy automatically from here. How about for the third one? Partial zx is this component that do have a function that it is the function of x. So I need to write it up. G minus beta y plus partial w partial x. And then the second term is equal to this component. So G times beta x plus partial w partial y, then plus the partial z, the third term equal to 0. Okay, so basically from the equilibrium equations, then we come up with is this equation here. And for this equation, why not we cancel out the g, okay, assuming that's isotropic. If it is not isotropic, for example, if that is general and isotropic, then you should know that influence will happen here. For non-isotropic material, that will be the function of positions, right? So that one you shouldn't drop this term. So again, for non-isotropic material, the only influence in the formulation is on the inclusions or exclusions of this term here. Good? Okay. So for this one, if you look at this one carefully, and that one should be leading to basically the partial derivative of this term is gone. The partial derivative of this term is gone. So leaving only the partial w. So that one will be equal to partial square w and partial x squared plus partial square partial y squared equal to 0, or simply is this one. Again, I believe some of your your class project on the other one kind of working on the last equation dissolution form, right? Hopefully. Okay, so that is the one. So to this point, we pretty much have everything we need, and that is combining strain compatibility, the strain displacement relations, then Hooke's law, equilibrium of the stress, compatibility, embedded that trivial in here. So basically here is everything we have. And so that is the general formulations for torsion of the prismatic shaft. And again, we under the three very rigorous, not restrictive assumption here. So the remaining is this: to solve for specific questions, we need to relate it to certain informations. For example, for this shaft, we have two kinds of boundary conditions. The first kind is on the circumferential surface, which means on the side surface of the shaft. The second boundary conditions happen on the top here, and where the torsion applied, assuming the bottom side is fixed. Okay. So here the remaining is we're going to relate it to the boundary conditions. Okay. The boundary conditions, the first one we can look at is on the circumferential side. Okay, so on the circumferential side, and for this case, basically nothing happened, nothing applied to the lateral surface of the shaft. So nothing there. So in boundary conditions, let me say we have the boundary condition 1, and for that case, basically for that case is something like this. How about let me start from the general one. How do you link to that point I want to address? how about this? I think I can do it. Assuming this is an element on a surface of the shaft, okay? I just make general. And this surface can be representing on the lateral side in this way, or can be on the top side. I just make that general. And for this formulation, assuming this surface has the unit normal vectors, and that is L, M, N, that is the unit, the outward normal vector on the surface here, okay? And we also know that on this surface, no externally applied force, or force, that means any kind of the force loading. And usually the people use the name called the traction to indicate unit force applied to, using traction to indicate the force applied to the unit area. So basically the people using this word basically indicating that is the force per unit area that had a similar concept of the pressure or line load. Okay, but basically indicating here, basically here we have no tractions. Basically here on this surface, the traction, for example, T1 and Tx and Tz and Ty equal to 0. Okay, so no externally applied. We simply use notation T as a traction. That's a 0. Okay. On the other side, we apply Cauchy's formula. We also know this one on the other side equal to the tau ij and multiply with n. N is L, M, M. Sorry, this one. Okay, this one is called the Cauchy's formula. Again, this appeared at the very beginning from the beginning of this semester. We know we can apply the Cauchy's formula to apply to the stress to determine the stress happened in an inclined plane. So basically this one equal to 0. Okay, so we implement this one. So let me borrow this one here. So here, let me just place safe writing. Okay, L, M, M. The terms equal to 0. So basically that indicating this term multiplied with this equal to 0. Okay, so that is in the x directions, and then this term multiplied with this equal to 0 in the y directions, and we interested in the third one. The third one is that one equal to 0. So for the third equation, let me write it up. G times minus beta y plus partial w partial x times L, and G and beta x plus w partial y times L m equal to 0. Okay. So you might ask me why, when we implement this equation, that will give us the equation 1 and equation 2 and equation 3. And here, this is our equation 3, right? And anyone be interested to why I'm not interested in the first two equations? The reason is this. Right now, I want you only on a cross section here, okay? If we would take so this is a profile of the boundary conditions, the profile of the cross sections, okay? Along any profile, we have the n equal to, that has the anything is the original cosine Lm. Along any profile, the third component equal to 0. So here, if we only focus on the cross section in 2 dimensions, basically leaving the end, this number equal to 0. So that reason, if we focus on the 2-dimensional plane, the first two equations basically is trivial. Okay? So we focus on this one. Right now, on the boundary condition, we focus on the profile here. So, okay, so basically we come to here. And then to this moment, we keep writing here. So this is the for on the cross section, this is the boundary conditions, and this is, let me call the form, form 1. Okay, we have a different form. And the second form could be this. We, in detail, we work on the L and M. If this is a point here, if this is a small argument, and let me call it ds, so this would be dx minus, and this is a dy, okay? So here, if we talk about the tangential direction, this is the ds, and this is the 90 degrees. And from this geometry, you should be able to tell these equivalents, this L simply equal to dx ds, dy ds. Let me see that one. Do I have anything L equal to dy ds? N equal to dx ds. Okay. Let me plug in this first, and if we have time today, I'm going to detail the reason why. So we simply plug in this one dy ds and n equal to minus dx ds into this form here. Then we have the different form. G minus beta y plus partial w partial x, and L equal to dy dx plus G beta x plus partial w partial y, and dx ds is a minus here due to this sign equal to 0. So this is our second form. In our form, for isotropic material, the G really can be cancelled out, so it's not necessary to write it. Okay. For this one, for the second form, we have further one is this partial w partial x dy, oh ds, sorry, ds minus partial w partial y, and dx ds is equal to beta and times 1/2 y dy ds plus x dx ds. Actually, this one is 1/2 beta and d ds x squared plus y squared. So this is the second form, and this is the first form. Depends on our derivations later on, and either we pick this one or pick this one. Depends on the availability of the given information about describing the boundary conditions. Okay, so keep those things in mind. The second boundary conditions is on the top here. on the top, all these stresses must be in equilibrium with the torsions. So how about let me write out here. So the second boundary conditions is this. On the top, okay, so that is the cross sections. Here is our torsion here. At any point, this is point xy. And here is the strain stress, zx direction. This is the strain stress, zy directions, okay? This is a small area, let me call the dA. The equilibrium in torque applications. So that means we simply make the moment about z directions must be equal to torque. Torque is this T is a given. This is the applied torque. Okay. So this one given is this. You see the small element or the torque produced by the small element integrating over the whole cross-section area. It must be equal to T. And what is the detail of the small torque here? So that one contributing by, again, look at this one. This is the coordinate x. And this force multiply, this is the stress, multiply dA, that is a small force. Let me do this one here. This is the stress, sigma zy times dA, that is a small force. This small force multiplied with this arm times x, this produce the counterclockwise moment, right? This is a small force, tau zx times dA, small force, multiply with this distance is y, the contributing counterclockwise directions. So how about this? Let me take the counterclockwise as the sign convention positive. So this is a positive term, this is a negative, so I put a negative here, and this is y. So the whole thing become like this. Good? Okay, then you plug in the two terms. We have already expressed the form here. Then that is the equations. And if you plug in here carefully, then you can see I'm running out of the space, but I'm going to try to insert it here. So this term equal to G times Zy. What is the Zy? X beta plus partial W partial Y. And this term equal to G minus Y beta plus partial W partial X, right? Good? Okay, so you look at here, plug in this one to here, plug in this one to here. Look at this term carefully. The integrand inside here, they contain beta, right? And of course, G will be there. And the remaining simply is a function of x, y, integrating over x and y with certain functions. Good? Good, right? Integrating the function of x, y over the dA, that can be done. That can be done easily by looking up the integration tables or whatever. So I can tell you, once we integrate this one, everything on the left-hand side will be G times beta times certain numbers. Let me call the number is J. J is the information about the size of this cross-sectional area and equal to T. Again, J simply is a result we implement to the very rigorous integrations of these integrations. So that means G beta times J equal to T. Next time we will come to focus on how to determine this one. Don't worry about this. But at this moment, I can give you a picture. We can determine beta equal to T times Gj. T is a given torque. G is the material properties you pick. J is the certain rigorous integration result, and that is a function of the geometry. That is a function of the shape of the cross sections. So to this moment, we solve beta. What is beta? Beta is this one. If we solve beta, then basically here everything is solved. Everything is solved except W. Good? Okay. So to this moment, the problem is almost solved, except what is a W? A W will be solved by this one. Okay. So eventually, I can tell the whole shaft, the torsion of the prismatic shaft, eventually is going to dedicate to the solution of the Laplace transform, not the Laplace equations here. Okay, and we don't need to go for that directions. For simple geometry, we have other quick way, and that's the reason for we have the two solution strategies. One is called the invariant solution method, the handout I give to you. And we have another approach I'm going to introduce. And to that moment, we pretty much finished the whole lectures for these semesters here. Okay. So next time coming back, I will get this writing prepared, and then talking about the solution process by dealing with W. And we have two strategies, and depends on which strategy we go forward, we have a specific solution procedures for each strategy. Okay, so next time we will focus on how to deal with W. Okay, thank you.